Okay, so today we're going to start with Anova, a one-way Anova, and the research question that we're looking at as an example is, to what extent do men and women's scores differ on your test variable? So my specific research question, putting in something for my test variable, is to what extent do men and women's score differ on test 15? So this is a difference test, looking at the difference in their means of their scores, and the score happens to be test 15. So here is the syntax for it. It's simple syntax, and there's several different ways, at least 3 different set of syntax for calculating Anova in SPSS, but we're going to use the GLM. Okay, so we have your test variable goes before the by statement. So I put test 15 here, but of course you would put your variable. And then the grouping variable, I have, when I demicode my gender, I always label the name of the variable instead of gender. I label it whichever one I called, either the man or the woman, whichever one I called the one. So in this case, I labeled ones as women, so I call this variable female, so that I don't have to remember later which one's a 1 and which one's a 0. So if you have it labeled as gender, of course you would use gender here, or if you have it as male, you would, whatever you coded it as. So your dependent variable is here, your independent or grouping variable is here. And so, and it also goes down here. So don't forget, when you're, if you're reusing the same syntax, make sure that you not forget to put it down here. Okay, so we have, if you want to point and click your way through, analyze, GLM, univariate. Once you get to the univariate button, you would move your 2 variables, your nominal female variable here and your test variable, your dependent variable there. Now, you might be thinking, well, you know that female is a dichotomous variable. You have men and women. So I could have used a t-test, that's correct, but I'm choosing to use an Anova, which is the same as a t-test, will give me the same information. The f is squared as opposed to the t. So when there's only 2 levels, like there is in gender, in a one-way Anova is equivalent to the t-test, except for the f will be squared as compared to the t-statistic. But we've talked about that before. Okay, so we've got our grouping variable, our dependent variable. We're going to click on options now, and under the univariate options, we're going to click on descriptives, estimates of effect size, observed power, and homogeneity test. And you can go ahead and move to display the means for overall or for by gender. But remember, we're going to run our descriptives, because we always run our descriptives, because we need to examine our assumptions. So don't forget, so here you would run your descriptives by your group, whatever your group may be, so that you can have the information by group. Of course, if you want the overall, then you would just eliminate the by statement, the by female, you would get rid of that, and it will give you the descriptives overall. So this is going to give us our box plot, it's going to give us our test for normality, it's going to give us our descriptives, it's going to give us confidence intervals, so don't forget you need to run your descriptives before you run your Anova and check your assumptions. So here are my descriptives, and this is the descriptives by gender. So here we have the 0 in the female category, which means male, and so we have our mean, standard error, confidence interval, standard deviation, skewness and kurtosis, and of course the other descriptives. But we take our skewness divided by standard error of skewness, which gives us our test statistic for skewness. Then we have kurtosis divided by standard error for kurtosis, gives us our standardized kurtosis, the test statistic for kurtosis. And so, of course, you do this calculation here to find out the extent of the deviation from normality. And we do the same thing for the women, and you can see that these numbers look fairly good. And here's our descriptive overall. And again, you can see the overall mean and the rest of the values. I didn't break out the standardized skewness and kurtosis because we needed it by group in order to test our assumptions. So here's our test of normality, and we have almost all of them okay, except for in the male category we show something in the KS test, but remember we use several indicators, and these look pretty good. Almost all of these look pretty good. When we look at our plot, our QQ plot for the men, here there does seem to be something going on at the tails, but it's fairly, I'd say it's looking pretty good. Here's the women, and it looks pretty good, so I'm going to say that is normally distributed enough, or does not deviate sufficiently from the normal curve. Here we have our Levene's test for equality, and it actually tells you underneath, it tells you what the null is, that the error variances of the dependent variables are equal across the groups. In other words, homogeneity of variance. And you can see that it is not statistically significant, which means that you will not reject the null, which is what you want to do. You don't want to reject the Levene's, because then that's telling you that the error variances are not equal. Okay, so then we are able to move on to our table here, which is the between subjects, or your Anova table. And you'll notice that it tells you what your dependent variable is, in case you forgot. And it tells you here what your grouping variable was. And this one-way Anova, female is our grouping variable. There's our error term. Then we have this final row, which is the corrected total, which is our regular total. Notice that I put the synonymous terms on the side here, so our independent variable, our grouping variable, also known as the between the model and the regression, and then the error term, variously known as the within error or residual. Depending on what output you're looking at, depending on what text you're looking at, it'll be named differently. So these are the three rows that we're concerned with in a one-way Anova. And there is your sum of squares, there's your degrees of freedom, your mean square, your F, and we look at our p-value and our eta squared, partial eta squared. Of course, the partial eta squared and the eta squared are equivalent in the one-way Anova. They're not equivalent beyond that, but in a one-way Anova they are equivalent. And it also tells you what your alpha is. Okay, so what can we conclude from looking at this Anova table? Well, that there is not a statistically significant difference between men and women on test 15. How can we conclude that? Well, the alpha is at 0.05. 0.128, which is the p-calc, or the p-calculated, or the statistical significance value. This is greater than 0.05. If it was statistically significant, it would be less than 0.05. So obviously this is not statistically significant. So, but remember, we always need estimates of practical significance as well. And so you use the Anova, the effect size spreadsheet that's available on my website. And on there, you just have to put in the values that are in green, and you'll notice that I did that here. You have two groups, because gender has two groups. The SS model, the sum of squares model, is 62563, that's the sum of squares model. Then the sum of squares total is 807593. Sum of squares total is 807593. Then you have the mean square error. There's the mean square, and the error is this row right here. And then you're done. And when you do that, you will get the percentage. In other words, I've already moved over the decimal for you 2 places. So you get the percentage for the eta squared and also for the epsilon and omega squared. So when you report your F statement, you would report F1, which is the degrees of freedom between, and then the 298, which is your degrees of freedom error, and then the p-value, 0.13, and then your eta squared and omega squared. Now notice that you need to stay consistent in reporting. If you're going to report 2 spaces after the decimal, make sure to do that. Also, there should always be a space before and after the equal sign. There should always be an italicized P, italicized F, and you should, for values that can exceed 1, they need to have a leading 0. So for example here, because I'm expressing the effect size in percentages, it can go from 0 to 100%. So in other words, I need to include a leading 0. Whereas the p-value, which goes from 0 to 1, so it does not exceed 1, so we would not report a leading 0 here. So make sure that you stay consistent with that according to APA rules. Okay, so let's go back to the research question that we had originally. To what extent do men and women's score differ on test 15? Well, we can look at the box plot and some descriptives to help us understand that. So we see obviously that their scores differ. The mean for the men was 78.59, the women 77.67. We look at the median, 79.78, and their standard deviations, the women's scores were a little more spread out. So their scores differ slightly. There's a small difference between them. However, as we determined from our Anova test, our one-way, the difference is not statistically significant, and the practical significance is minimal. It's our uncorrected value, and our corrected value is less than 1%, less than 1%. You know, here we have, if we go with our corrected value, less than 0.5%. So I think that is sufficient to be able to state, you know, you would write your descriptives, you would write that their difference is slight and it is not statistically significant, and the practical significance or the effect size is minimal. So let's consider another variable, a different ANOVA. Let's consider this variable cohort, which actually has 3 levels as opposed to gender, which had 2 levels. So you have cohort 1, 2, and 3. I'm going to look at test 15 by those 3 cohorts. And you use the same syntax that you had before. Don't forget you would do your descriptives and then your ANOVA. And you would run through the exact same process that we had before. In other words, you would click through exactly the same, except for the differences. Instead of having female here, you have cohorts. You'd go through your options and click on those values there, and you end up with the syntax that you have. You'd go through your descriptives, look at your assumptions for normality and for Levene's, and then you would end up with your ANOVA table for this new syntax. And here's the ANOVA table. So we have our test of between subjects, and again the variables that we would be interested in, or not the variables, excuse me, the rows would be these 3 rows right here. And in contrast to the previous ANOVA table, this one demonstrates that there is a statistically significant difference in the levels of cohort in terms of their test 15 score. So with gender, when there was only 2 levels, men and women, there's no discussion about, well, where does that difference lie? Remember that the ANOVA hypothesis is mu1 is equal to mu2 equal to however many means you have. In our present study, in this one that we're looking at here, we have 3 groups that we're looking at. So when we find a statistically significant difference, we do not know if that difference is between 1 and 2, between 2 and 3, between 3 and 1. We don't know, because all that Anova does, a one-way Anova here, it's an omnibus Anova. It's testing it's testing the equality of all the means. So if there's a difference, it could be that they're all different, or one is different from the rest. And so you have to do something beyond just looking at this to determine where that statistically significant difference lies. And what we do is a post hoc test. Of course, never do a post hoc test when you only have 2 levels, because it doesn't make any sense. Because if you only have 2 levels, obviously the difference is between those 2 levels. When you have more than 2, that's when you need a post hoc, if you have statistically significant differences. Obviously, you would not do a post hoc test if there is no statistically significant difference, because then what you're asking is, there was no difference, but let me find out where the difference is. And that doesn't make any sense. You would only do a post hoc if you find a statistically significant difference. Okay, so we did find a statistically significant difference for the omnibus Anova. We do a post hoc test. So you'd click on that option right there. When you do that, you'll get this window right here, and you need to move your variable into post hoc test 4. Of course, we only have one variable that we're testing here, but if we had more, you would move the ones that you wanted a post hoc test for. So I moved that there, and I want the Tukey and the Spss. Remember, the Tukey is the one that gives you simple pairwise comparisons, where the Spss is available, or makes available the complex contrast. So then you click through, and don't forget you do your options, just as you did before. Let me show you to remind you. That's at the top of that sheet. Remember, you have your options. So then you get this syntax right here, which is identical to the syntax you had before. In fact, you don't have to go through all that clicking if instead you just want to put in this syntax into your underneath the intercept line and before the print line. So that will allow you to get the post hoc test. So let's look at what that looks like. So here is a table of multiple contrast, multiple comparisons, and you've got the Tukey and the Spss, which is what we requested. And notice that I highlighted here for you the statistically significant ones. Could also highlight that, but it says the same thing, because what it's saying is there's a statistically significant difference between 1 and 3, not between 2 and 3, you'll notice, because that difference is not statistically significant. There's not a difference between 3 and 2 again, but between 1 and 2, and so that shows that. It shows it here also, of course. And the Spss allows for all possible linear combinations, not just pairwise, should you need that. But so in this case, in our simple case here, the results are identical, and what this is telling us is that cohort 1 differs from 2 and 3. But cohort 2 does not differ from 3, but cohort 1 differs from 2 and 3. So let's look at the descriptives, and you can see that cohort 3 is at a 79.4, cohort 2 is 78.3, and so these are fairly close to each other, and according to the post hoc, 2 and 3 are not statistically significantly different from one another, but cohort 1 at a 76.61 is distinct from cohorts 1 and 2. And that's what the post hoc test is telling you. It's telling you, because remember, I obtained a statistically significant difference in the omnibus Anova. So that means somewhere in here there's a statistically significant difference. But I did not know prior to conducting the post hoc test where that difference was. But now I do, and I know that difference lies in cohort 1 is different from 2, and cohort 1 is different from 3. So Again, you would only do post hoc test when you find a statistically significant difference. If you do not find a statistically significant difference, do not do a post hoc test. And if you find that your grouping variable is only 2 levels, of course it makes no sense to run a post hoc test because you already know where the difference lies. Okay,